Thus far, we've talked about single objects. And we've talked about how a single object would move or accelerate due to a force being applied on that. What we want to know now is where these applied forces come from. For example, if we consider a system where you have a hammer and a nail, we might be talking about where the force on the nail comes from in order to drive the nail into the wall. Well, when the hammer hits the nail, that hammer exerts a force onto the nail. However, if we're looking at the other situation, if we're looking at the other object, the hammer, we could say that the nail exerts a backwards force on the hammer as well. And so when we're talking about the forces acting on an object, we're seeing that these forces often come as forces of interaction between the object we're interested in and other objects in its environment. If you don't, to show this idea, imagine hitting the nail with a glass hammer. In that situation, the glass hammer would shatter. The reason that hammer is breaking is because of the force that the nail is applying back to the hammer. Similarly, imagine playing catch and catching a baseball. As you catch the baseball, you're applying a force on the ball to slow it down in the space of a fraction of a meter in your glove. And at the same time, you feel that force, the force of the baseball pushing on you. You feel that in your hand. And if you play catch without a glove, for example, your hand can really hurt, can be really sore due to that force of the ball on your hand that is balancing out the force of your hand stopping the baseball and catching it in your mitt. Considering a few other examples, if you have a baseball being hit by a baseball bat, the bat is applying a force onto the ball, and the ball is applying a force back onto the bat. Another example is if you're playing a tug of war. You're pulling on one end of the rope, the other person feels your pulling on their end. As they pull, you feel their force back at your end of the rope. We've seen this in other situations as well. When you push down on a chair when you're sitting in it, the chair pushes back up on you and gives you a normal force. In each of these situations, we have what is called an action-reaction pair. These forces occur simultaneously, so it's impossible to say what the action and the reaction is. But typically we look at the action being acting on the object we're interested in, and perhaps the reaction is another force on an object outside of the system in general that we're not as interested in. So what we've seen here is that if an object A exerts a force on an object B, then B exerts a force back on object A. That's what we mean by action-reaction pair. So if we're pushing two blocks together, for example, and we have a force here that our block A is pushing into block B, that means there has to be a force going the opposite way as well, that A feels like it's being pushed by B as well. This idea is enshrined in Newton's third law. It says that every force exists as one member of an action-reaction pair of forces. That these two forces act on two different objects, and that these force members are equal in magnitude but opposite in direction. So we typically see it as the force of A on B is the negative of the force of B on A. Here the negative sign reverses our direction. This is the more scientifically correct and technically correct definition of Newton's third law. However, the way it's known in popular culture, and a good way to remind yourself, is to say that for every action, there's an equal but opposite reaction. For every force, there's an equal force, but a negative and opposite direction force due to that initial force. And Newton's third law comes into play in many situations that we'll see shortly. Imagine, for example, trying to walk across a frictionless floor. As you walk, you have to push off with your back leg, and basically as you push backwards with your leg, your foot must stick to the floor, and that pushes your body forward. If you're in a situation of being on a frictionless floor, if you push your leg back, there's no traction, and so your foot just slips around. This is what happens on an icy day and you're stuck on a sheet of ice. It's very hard to stand or to walk, because whenever you try to push to the side, you have no traction, no friction with the ground. So if we imagine this guy who's trying to walk, he's trying to apply a force backwards. He's pushing backwards with his back foot in order to make himself go forward. And we just said if there was no friction, he would just slip and slide all around. But when you're walking regularly and normally, applying this force backwards pushes you forwards. And so we say that the force that resists motion, that resists his foot slipping and doing nothing, has to be static friction. And thus, static friction here points in the forward direction, and it's what pushes you forward. Basically here, he's applying a force backwards, and there's a force of friction that pushes him forward as a reaction to that. If that friction weren't there, if it were ice, for example, his legs would be going out in all directions, and it would be very hard to stand up. We see the same idea many other places. For example, if you have a rocket, we've talked about there being a thrust on the rocket, which is due to, which is what pushes the rocket forwards. What's actually happening is that the rocket is pushing its exhaust out the back. And as the rocket pushes the exhaust backwards, the rocket is pushed forwards with thrust as a result. And so you have an action-reaction pair there. Similarly, when you have a car on the road, it works similarly to the person walking. If the car was on ice, the car wheel is going to try to spin. And if you're on ice, the car wheel will just spin, there'll be no interaction with the ground. When there is friction, however, the car wheel is trying to spin like this, and so friction will have to be in the opposite direction. Friction will oppose this direction of motion, meaning that there will be a force of friction that will point forward, which is what propels a car forward as well, as this idea of static friction pushing us along. Finally, we have this idea of gravity. We saw this a little bit in the previous chapter, and we'll see it a little bit more here. We know that when you release a ball, it will fall down due to a force on the ball that comes from a gravitational attraction to the Earth. But we've just said that if you have action-reaction forces, they should be equal and opposite in magnitude, meaning that if there's a gravitational force on the ball downwards, there should also be a gravitational force on the Earth that is upwards. We know that the force of the Earth on the ball is going to be the same as the gravitational force on the ball. And so if we want to know what the acceleration of the Earth is in this case, the acceleration of the Earth is the force on the Earth divided by the mass of the Earth. Here the force on the Earth is the same magnitude as the force of gravity on the ball. We see that the acceleration on the Earth will then depend on the ratio of the two masses times our value of gravity. So if the ball has a mass of 1 kilogram, the Earth accelerates as well. The Earth accelerates with an acceleration of the order of 10 to the negative 24 meters per second. So it's imperceptible, but it is there. This means that the joke that when Chuck Norris does push-ups, he doesn't push himself up, he pushes the Earth down, that's actually exactly correct. That's what we're seeing here. That's just true with everything and anyone. This is also a small amount here, but there are other situations where you have multiple, you have a binary star system, for example, and you have two different stars that rotate and orbit around a common center of mass. And so in that situation, you can have two binary stars that are both pulling on each other gravitationally, and that causes them to follow a circular path around a common center of mass, rather than one orbiting the other like we have with the Earth and the Moon, or the Sun and the Earth, both of which contain objects where one is much, much greater in size than the other one.